Hello, this talk is for the paper Contention Resolution with Message Deadlines. This is joint work with Kunal Agrawal, Michael A. Bender, Jeremy T. Fineman, and Seth Gilbert. I'm Maxwell Young and I'll be presenting. Contention resolution addresses the problem of coordinating access to a common resource. Often this resource is modeled as a multiple access channel or a shared channel, and we talk about this problem in terms of players that each have a message they need to broadcast on this shared channel. However, only one player can broadcast successfully at any given time. Here we have Calvin doing his important broadcast, but there are many other applications, including to wireless communication, shared memory, and congestion control. And so it's not surprising that the contention resolution problem has received a lot of attention from the research community under a variety of models. Here, our players are treated as jobs, and these jobs arrive over time seeking access to the shared channel. This is a time-slotted setting, and there is no global clock. That is, the jobs don't share a common notion of time a priori, and they don't know how old the system is when they join. Each job has a data message, which requires one slot to send. Here's an example. We have Calvin arriving at some point in time to access the channel and deliver his important data message. Of course, the old telephoning network, I guess, had dedicated non-shared channels, but whatever, it's a funny comic strip. Finally, in addition to its data message, a job may also send control messages to aid in coordinating access to the channel. The channel provides the following feedback on a per-slot basis. If no job sends in the slot, then the slot is empty and any job listening to the channel can determine this. If the slot contains a single broadcast, then we say the broadcast is successful. All other jobs can hear this message if they're listening to the channel, and the sender knows it was successful. Finally, if two or more jobs send on the channel in the same slot, then none of these broadcasts succeed, that is, they all fail, and this is often referred to as a collision. Any job that listens will hear noise. It could differentiate this from the case of an empty or successful slot. These cases are illustrated in the figure. Time is moving from left to right, broken into time slots. The colored blocks indicate when a job broadcasts. Each slot is marked as empty, success, or failure to illustrate the feedback that jobs would receive. Each job J has a release time, Rj, that is the slot index when it arrives, and a deadline, Dj. The time slots spanned by Dj minus Rj are referred to as job J's window. A job doesn't know Rj, rather it only knows that it has arrived and how long its window is. Deadlines add an online scheduling constraint to the contention resolution problem. Each job aims to successfully send its data message sometime in this window. The scheduling constraint seems like a natural extension to the contention resolution problem. For example, deadlines align with prioritization of network traffic, which is one aspect of quality of service. A common example is delay-sensitive traffic, such as voice over IP, or perhaps more importantly, traffic associated with first-person shooter games. Additionally, real-time communication protocols used in some industrial systems may require data from a sensor to be delivered within a certain time frame in order to be useful. So our incorporation of deadlines is motivated by these sorts of issues, and this is not an aspect that has received much attention in prior work on contention resolution. Given this problem of contention resolution with deadlines, something that seems worth aiming for is to have each job succeed in sending its data message with high probability. Prior work by Bender and co-authors has shown that for online job scheduling, dense instances, where many jobs arrive with deadlines that are concentrated over a short period of time, can lead to high resource costs in finding a solution. This motivates us to consider, like them, instances that are not too dense. To formalize this notion of not too dense, we use the concept of gamma slack feasibility, which means that a feasible schedule of the jobs exists even if we enlarge each job by a factor of 1 by gamma, where gamma is some value less than 1. The smaller that gamma is, the sparser the instance. Here we find that we can obtain our desired result without gamma depending on the number of jobs, n. Some sufficiently small constant suffices. So this is the goal. For constant slack feasible instances, each job should succeed in sending its data message with high probability. One last thing that we haven't defined is with high probability in what. but we'll get to that in a moment. To address our problem, an obvious starting point is for each job to broadcast in a slot chosen randomly from its window. We call this simple algorithm uniform. And you can imagine there are variants where, say, some constant number greater than 1 slots are chosen by each job to broadcast in, but the main findings hold. So for simplicity, we'll just consider a single slot that's chosen by each job. To analyze uniform, we need to formalize the notion of contention, and this is a standard definition in the literature. For job J and slot T, we use P sub j of T to denote the probability that job J sends in slot T. Then, for slot T, the contention C of T is the sum of the sending probabilities over all jobs for that slot T. The probability that any job successfully broadcasts in slot T, this is denoted by P sub success of T, is a function of the contention, and the 3 useful relationships are given here. In particular, we can highlight this third relationship, which says that when contention is large, the probability of success is exponentially small in the contention. So back to uniform. To give you the good news first, for constant slack feasible instances where gamma is a sufficiently small constant, a constant fraction of jobs will succeed with high probability in n. This is great news. Unfortunately, there is bad news, which is that there are jobs that have probability of success which is polynomially small in n. In other words, there are some jobs that will starve. It's useful to sketch the intuition for why this can happen. Imagine that each job J has a window of size J. Then if you consider the execution of uniform, you can see that the contention in the first slot is the sum of the harmonic series. So the contention is roughly logarithmic in n. This is true for many jobs. If we look, for example, up to job square root of n, the contention is still theta log n. And you can make this argument tighter if you wish, but the point is that the probability of some job succeeding is polynomially small in n by the relationship between contention and the probability of success that I highlighted earlier. So from this sketch of the analysis, you can see the really bad news. Those jobs which starve are likely the jobs with small windows, and these are the jobs that are probably the most urgent. Instead, we'd like things to be more fair. For large windows, there's plenty of time and no reason to fail. For small windows, these are more constrained jobs, but their probability of success should be commensurate with their window size. In other words, even jobs that have small windows should have a decent shot at succeeding. So we need another approach. Given this look at uniform, we're now ready to specify our goal in full detail. For constant slack feasible instances, each job should succeed in sending its data message with high probability in its respective window size. For the rest of this talk, I'll describe how we obtain this result. As an intermediary step, we temporarily assume that windows are power of 2 aligned. That is, each job's window size is some power of 2 and has a release time that is a multiple of that window size. We need the notion of a job class, which is the set of jobs that have the same window. So, job class L is made up of those jobs belonging to the same window of size 2 to the L. The critical time for a job class's window is simply the first slot of that window. The broad strokes of how jobs become active is as follows. At any given time, at most a single job class will be active, that is, attempting to send their respective data messages. Jobs and other classes will be listening and simulating classes with smaller windows. The critical time, again, the first slot of a job class's window, demarcates a point when a new job class might become active. This is where a class with a larger window will pause and listen for the presence of a class with a smaller window. Once these smaller window job classes are completed, then the suspended larger window class can reactivate and continue. So, what are the jobs in a job class doing while they're active? There are 3 main activities. The first is estimating the number of jobs in the class. This runs in time polylog of the window size, or poly-L. This estimate is accurate to within constant factors with high probability in the window size. Once an estimate is achieved, it is used to set the number of steps for making broadcast attempts for those jobs in the active job class. Finally, those jobs that do not succeed in this time for broadcasting give up, and this is referred to as truncation. but with high probability in the window size, a job class should avoid truncation. To illustrate what's going on here, we can use an example with 3 window sizes, and note that these windows are power of 2 aligned. The job class with the smallest window is active, while those classes with larger windows above, middle, and top are suspended, and they listen and simulate the active class. That is, they observe the estimation activity whose slots correspond to the yellow boxes in the figure. The middle and top classes then know for how long the corresponding broadcast component will run. These slots correspond to the blue circles. After that point, they know that either all jobs in the class have succeeded or will truncate, and the middle job class can start executing its estimation and broadcast activities. When the next critical time occurs, the middle job class is interrupted and must suspend again to listen. In this case, there are no jobs in that class to worry about, none arrived, and listening for 2 slots is sufficient to convey this information to the larger window classes. So the middle job class reactivates and finishes its broadcast activity. And now the top level job class can start executing, and so on. The intuition for why this channel access scheme works is as follows. Consider, say, the middle job. Given sufficient slack, the nested smaller window classes can run their respective estimation and broadcast activities to completion while not taking up more than a constant fraction of the middle job class's window. This leaves sufficient time for the middle job class to execute its own estimation and broadcast activities. So, assuming power of 2 aligned windows, we can get the result that we want. But, of course, the big question is, how do we go about removing this assumption? For this case, we need a few things. First, for any arbitrary window W, trimmed of W is the largest aligned window in W. Related to this, for a set of jobs J, trimmed of J is a set of jobs where the window W for each job is replaced by trimmed of W. A prior result from Bender and co-authors states that the slack feasibility of an instance is preserved to within a constant factor under this trimming. So, now things would be great if we had a global clock. Jobs would know their arrival time, could trim their windows, and we'd have job classes and critical times and everything that we need to run aligned. Unfortunately, we don't have a global clock, so what do? Our solution is to elect a leader to keep track of time. At first, this may seem like we're starting from scratch, since leader election and contention resolution are tightly coupled problems, but bear with me. The first and easiest problem to start with is how should jobs coordinate leader election? That is, jobs may arrive at different times, and at the very least, they need to know if a leader exists, and if so, the time or clock value being advertised. If not, they need to allocate slots to elect a leader. So this is a problem of local synchronization. To handle this problem, we can reserve slots in a way that allows jobs to determine which slots correspond to which purpose. We have 4 slots as illustrated here. The timekeeper slot is used by a leader, if one exists, to broadcast a notion of time. A leader will also include its own deadline in this broadcast. This allows jobs to know when that leader is scheduled to depart so that another leader can be elected before that happens, if need be. The align slot is used to run our aligned algorithm that we discussed previously. The leader election slot is used to perform leader election, and the anarchy slot is for the case where a leader fails to be elected. More on that in a moment. We also reserve 2 consecutive synchronization or sync slots that are always non-empty when there are active jobs. And finally, we put in alternating guard slots so that when local synchronization is in place, the only location where 2 non-empty slots occur are the sync slots. This allows a newly arrived job to listen for 10 consecutive slots and determine what is happening. If 10 slots go by and there are no 2 consecutive non-empty slots, then it can start broadcasting in the sync slots, thus setting in place the local synchronization. The second, harder problem with handling the general case is the election process itself. If jobs attempt the election process by broadcasting with a reasonable probability, say even if this amounts to sending roughly once before the respective window ends, then there is too much contention and the election will fail. But if jobs send at a lower probability, They may not send at all before their window ends, and again, the election will fail. So we seem to have a problem. A leader is needed, so all jobs get a fair shot at the channel, but to perform leader election, jobs need to have a fair shot at the channel. This is circular. Our solution involves noting that there are cases where not having a leader doesn't hurt us. More on this in a moment. Say a job arrives. In the case of no leader, or when there is an old leader relative to the new job's deadline, we use what we call the Slingshot protocol. This protocol has a pullback stage, which makes use of the leader election slot that we described earlier, and then a release stage, which makes use of the anarchy slot. The pullback stage involves the job sending with low probability in its window size, that is, 1 by W polylog of W, in the leader election slot, and otherwise listening. If the job succeeds in sending, then it knows it's the leader. Going forward, it will send in the timekeeper slot, sending both the round number and its own deadline. Any old leader can gracefully step aside. Otherwise, a different job becomes leader. That's fine too, but regardless, anyone else runs aligned in the aligned slot. A job will run the pullback stage for a number of slots which is polylogarithmic in its window size. If no leader is elected by this point, then the job greatly increases its broadcast probability and attempts to succeed in broadcasting during the anarchy slot. This is the release stage of the Slingshot protocol. Interestingly, if there are at most O of W by log cube W jobs with the same window, then the contention from the release stage is okay, and the anarchy slot has mostly constant contention, so here a leader is not necessary. Otherwise, if there are omega W by log cube W jobs with the same window, then a leader is elected with high probability in the size of the window. At this point, again, jobs can now use aligned. These ingredients, synchronization, slingshot, and aligned, give us our algorithm PUNCTUAL that handles the general case and provides us with a guarantee we wanted. That is, for constant slack feasible instances, each job succeeds in sending its data message with high probability in its respective window size. So that's it. Thank you for listening, and I'll see you in the Slack channel, assuming anybody shows up and I can figure out how it works.